All right, let's dive into an incredible, invisible world. It's the force that, zaps you when you touch a doorknob, but it's also the fundamental force that holds the very atoms of your body together. This is electrostatics, the unseen architect of our entire reality. You totally know this feeling, right? You're shuffling across the carpet in your socks, you reach for a metal doorknob, and zap! You get that tiny little shock. Well, that little spark is actually a miniature lightning storm, and it is our first clue into this powerful, hidden world we're about to explore.
So to really get what's behind that spark, we have to go right to the source. We've got to meet the main character in this whole story, electric charge. It's this basic, fundamental property of matter. And believe me, it is the hidden engine behind pretty much all electrical stuff.
So what even is charge? I mean, it's not something you can hold in your hand. Think of it like mass. It's just a built-in quality that matter has. It's the thing that lets matter create and respond to electric and magnetic forces.
And where does it come from? Well, it all starts deep inside the atom. See, atoms are usually perfectly balanced, with the same number of positive protons and negative electrons. But they can lose or gain those little electrons. If an atom loses an electron, suddenly it has more positive stuff than negative stuff, and we say it's positively charged. And if it grabs an extra one, you guessed it, it becomes negatively charged. It is all about the movement of these tiny electrons.
And this leads us to the single most important rule in all of electrostatics. I mean, if you remember one thing, this is it. Charges that are the same, like two positives or two negatives, they push each other away, they repel. But opposite charges, they pull towards each other, they attract. This one simple idea, opposites attract, likes repel, is going to govern everything we see from here on out. Okay, but this whole pushing and pulling thing isn't just random chaos. It turns out that all electric charge has to play by a very strict set of rules. Unbreakable laws, really. So rule number 1, charge is conserved. You can't just make it out of thin air or destroy it, you can only move it around. Rule 2, it's quantized. Now this just means it comes in tiny individual packets, the exact size of a single electron's charge. You can have one of these packets, or a billion of them, but you can never, ever have half a packet. And finally, charge can't just float around on its own, it has to be carried by something that has mass. You know, a really great way to get a handle on charge is to compare it to something we all know, mass. Mass is always positive, right? And its force, gravity, is always attractive, it only ever pulls. But charge is special. It can be positive or negative, and that means its force can either attract or repel. That two-sided nature is what makes electricity so incredibly powerful.
So we know that charges push and pull on each other. But how strongly? Is there like a master blueprint that tells us exactly how this force works? Oh yeah, bet there is.
And what's amazing is how simple it is. The strength of this electric force really just boils down to two things. First, how much charge you're dealing with. More charge means more force. And second, how far apart they are. The further you pull them apart, the weaker that force gets. That's it.
And it is all captured perfectly in this one beautiful equation, Coulomb's law. This thing gives us the power to calculate the exact force between any two charges. It gets stronger with more charge, and it gets way, way weaker as they get farther apart. And this isn't just a guideline, it's a universal law. It works everywhere, from inside a single atom to clear across the cosmos.
Okay, but this brings up a much deeper question. I mean, we know these charges are pushing and pulling on each other, but how are they doing it across empty space? How do they touch without actually touching? Well, the answer is one of the coolest concepts in all of physics, the field. Seriously, think about that for a second. If you have a positive charge just sitting there, all by itself, how does it instantly know that you've just placed a negative charge a few feet away so it can start feeling that pull? There's no string connecting them. So what's the messenger?
The messenger is the electric field. Every single charge creates this invisible field of influence that radiates out into the space all around it. It's like an invisible web that actually changes space itself. So when you bring a second charge into that field, it's the field right at that spot that tells the charge which way to go and how hard to push.
Physicists came up with a great way to visualize these fields using what they call field lines. For a positive charge, the field lines always point straight out, away from it. You can imagine placing a tiny little positive test charge anywhere near it. These lines show you exactly which way it would get pushed.
And for a negative charge, well, it's the exact opposite. All the field lines point inward, toward the charge. They create this beautiful map that shows the direction a positive charge would be pulled. It's literally a picture of attraction.
Now this is where it gets really, really cool. When you bring a positive and a negative charge near each other, their fields merge. The field lines literally flow from the positive charge and curve around to land on the negative one. It's like they're reaching out and connecting. This is a literal picture of what the force of attraction looks like.
And now, look what happens when you put two positive charges together. Their field lines bend away, actively pushing each other apart. They never cross. You can almost feel the tension in the space between them. It's just a stunning way to visualize that repulsive force.
So Coulomb's law is fantastic for a couple of simple charges. But what if you have charge smeared all over a complicated shape like a metal ball or something? Trying to calculate the force from every single little bit of charge would be an absolute nightmare. For messy situations like that, physicists have a secret weapon.
Yeah, instead of adding up billions of tiny forces, which is just way too hard, there's a much more elegant and powerful way to think about the relationship between a chunk of charge and the field that it makes. And this powerful idea is called Gauss's law. All it asks is that you imagine drawing a bubble, any kind of bubble, around some charges. Gauss's law then says that if you just count up the total number of field lines poking out of that bubble, that number is directly tied to the total amount of charge you've trapped inside. It doesn't matter how the charges are arranged, just what the grand total is. It is an unbelievably clever shortcut. Now, this formal statement might look a little complex, but the idea behind it is profound. It's this deep, beautiful connection between the shape of the field, the lines poking through a surface, and the thing creating that field, the charge itself. This concept is an absolute cornerstone of how we understand electricity and magnetism today.
So from a simple spark on a doorknob all the way to the invisible laws that govern these force fields, we've seen the power of electrostatics, the study of charges when they're just sitting still. But that leaves us with one last, really big question. What happens when these charges stop standing still and start to move? Well, that is where our world gets even more interesting, and it's a story for another time. Thanks for listening.